first of all, introduction. Hello everyone, I'm Roberto-Rafael. I'm currently finishing my PhD in economics at the LSE. And I'm going to present some work that I did while I was an intern at Google DeepMind on social choice theory. I mostly work on societal impacts economics and a lot of LLHF and AI safety and alignment. So if you're interested in those topics, grab me, and I'm always super happy to have a coffee and a chat. So yeah. So this is as I said, this is a work that I did during my internship. And of course it was thanks to my amazing collaborators, Mark, Francesco, and Kate. Everything that is good in this paper is thanks to them. If there's any mistakes, blame me, and please feel free to throw questions at any point during the presentation. I'm always happy to interrupt the presentation and clarify things. Feel free to ask for clarifications, questions, rebuttals, whatever. So I'm going to start with the too long didn't read punchline. What we do in this work is, we criticize LLHF using voting systems theory, and we see there's some known problems about how LLHF converges to situations where you could have answers that are not the answers preferred by the majority. Imagine this a scenario where you ask this question and people have these particular preferences. If you train an LLM with LLHF, it will converge to a situation where it says something that is not the thing preferred by the majority. And there are alternative methods that are based on social choice theory, voting theory, that converge to better solutions in some normative way. Okay, so of course, disclaimer, the views and expressions and the views and opinions that I will express here are just my own and do not necessarily reflect the views or opinions of Google DeepMind. I have to this is all just our personal opinions, and the normative statement are my own. So first of all, for those of you who are not familiar with social choice theory, this is a theory of voting that has started to get some traction in certain labs. So these are some particular statements made by Anka Dragan, the head of the alignment at DeepMind, and Amanda Askell, also the head of alignment at Anthropic, on how social choice theory seems like a very good direction to approach the problem of alignment. But yeah, then there's the question, okay, what is social choice theory? Roberto, I've never heard about this. Can you explain it to me? So I'm going to assume that you've never heard this topic. So social choice theory is a theory about making collective decisions. It's a mathematical theory about voting systems, and a voting system could be a system used to decide something as classical as who should be our prime minister, or hey, our team achieved a milestone. What should we eat, right? Or maybe it could be the method that we could use to decide what should the LLM say, or what should an agent do, right? Just as a motivation, here I'm thinking about agents that make decisions that will affect a lot of people, where people disagree on what is the best thing to do, right? The problem of personalization, it's kind of you could think about it as a sub-problem. I'm not going to focus so much on personalization. I don't think that the two are because I always get the criticism of if I'm chatting with my chatbot, should it answer the democratic answer, or should it answer according to what I want? And I'm okay, yeah, fair enough. I think this should answer what you want, but for the sake of the argument, I'm going to focus on the problem of LLM does something that affects a lot of people, what should it do, right? But at the end of the presentation, I'm going to attack those limitations and so on. So just hold on with me, but feel free to ask for clarifications and interrupt me at any point. But yeah, motivation, LLM in the future has to make decisions that are going to affect people. What should they do, right? Okay, so to put the framework clearly in words, the situation is the following. We have a set of candidates, options that we have to choose from. Imagine that we all here at ODYSSEY have to share ice cream. There's only, we can only buy one huge ice cream and we will share it all together. And there's only 3 flavors that we can choose from: chocolate, vanilla, and strawberry. Every single one of us has a ranking over the flavors, okay? And what we want is a method, an algorithm, a function, a voting system that goes from all our preferences over the ice creams to a unique ice cream flavor that we will choose, and that's the thing that we will buy, and that's the thing that we will share all together. So just to make it more concrete, let's talk about something where people have a lot of disagreement. Which one is the best starter Pokemon? And I'm going to show that the idea of like using a voting system is not such a trivial question. There's some classical voting systems that have a lot of problems, and the one that I'm going to talk about is the one that most people are familiar with, which is called plurality. So what is plurality? Okay, imagine you have to make this decision, and you have your own particular ranking. I'm going to use the colors red, green, and blue because not everybody is as nerd as me. And assume that you have this particular ranking, and then when deciding which one of the three is the coolest, collectively, you know, in this democratic system, what we're going to do is we're going to ignore our second and third preference, and I'm going to focus on our first. We're going to go to the voting station, we're going to write it on a paper, and we're going to put the paper on a box. And then at the end of the night, imagine the following situation. Imagine a society where 45% of the people have this particular ranking, they would vote for red. Then imagine in this particular example, 35% of the people have this other ranking, then they would vote for blue, and then if the rest 20% has this other ranking, they will vote for green. Okay? In this particular example with plurality, we only focus on the first option. We end up having at the end of the night this result, and then we'll be like, red wins. Red is the best option. Everything clear. This is the most classical voting system, plurality. Problems with this system if we decide to use voting systems in a naive way. Well, red is the worst option according to the majority of people. And in this particular example, it seems that green should win all pair comparisons. It's known as, sorry, green is the best option because it wins all pair comparisons. It's known as a Condorcet winner. What do I mean? Well, if you focus your attention between green and blue, green is preferred to blue by 65% of the people. And green is preferred to red by 55% of the people. So there's like this kind of property kind of like hints to us that it feels that green is the desirable option in some way, right? Like green is the Condorcet winner, green should win. We should have a voting system that satisfies Condorcet consistency. Okay. Also, I will die on this hill. Objectively, Bulbasaur is the best option because it evolves faster and it has advantage in the first few games. But let's keep that heated debate for later. So why is social choice theory relevant? Well, we keep talking about we should align. Oh yes.
You said it's objectively better. According to which criteria is it?
This one?
These two. These are very specific criteria. So, is it in which sense is it objective?
Oh, if you play the Pokemon game like it evolves faster and you have advantage because it maximizes the stats earlier, and in the first two gyms you have some advantage on the. This is just a joke, by the way, like just to make it super clear. But like it has advantage to the first two gyms because this is plant type, and the first two gyms are rock type and water type.
Because I have no idea what Pokemon. My question.
Yeah.
If there's a.
This is just a joke. It's like you can ignore it, but.
Sure, but my question is there an objective way?
No. Sorry.
Right.
It's not objective. It was just a joke. Ignore the. You could ignore this slide. It's not objectively the best one. Yeah. I'm just messing with you all. I also think that Charmander is cooler, but it's a cool fun fact. Anyway. Anyhow, I always get someone asking me about that slide. Like, no, Charmander is the one who should win. What does it mean? Okay, so going back to, what does it mean to align to human values? There's kind of like, I feel that sometimes when I chat with people in the field of alignment, there's kind of like this implicit assumption that some people have that is like, oh, if you just sit down and you think for long enough and we could have debates for long enough, we would arrive to this true set of values, and that's what the LLM should align to. And again, this is a philosophical point, but like maybe that is not the case. Maybe people truly have different preferences over things, even if they have the perfect information and they think for long enough and they debate for long enough, they would just like, dude, I prefer dogs, you prefer cats, and that's fine, right? And if that is the situation, we still have to make a decision on like what should the LLM align to. And right, like then the question is like, okay, when we align the LLM, whose values do we choose? What do we do when there's conflicting opinions on what's the best thing to do, right? And it feels that using voting system in some way and social choice theory in some way is very relevant. So in my mind, ideally in the future, when the LLMs, are answering questions that are, relevant for important decisions that affect people, what they should do is, and this is in the abstract, but I'll be more concise later, they should, look at, okay, what's the next token that I should give? They should look at the preferences of all individuals over all possible answers. They should use a voting system to aggregate those preferences, and then they should answer, the answer that you will get if you use this voting system. Is the setup clear? Any questions about the setup so far? Yes?
Are you talking about doing this during training or inference?
Sorry?
Are you talking about doing this during training or inference?
It will be during training. Yes. Yeah, the idea is that I have preferences and then I convert to something during training that is equivalent to this. Yes. Yeah, I'm not saying that during inference we should emulate the voting, but thank you, yeah.
So are you talking about trying to generate a distribution that matches
Yes.
the underlying preferences, or just like full probability on the best option according to some social criteria?
I'm talking about you converge. So yeah, I am talking about I would hope that the LLM converges to something that gives the same results that you would get if you did the voting. Does that answer the question? Yeah.
Yeah.
Okay. So I'm not doing the voting at inference time. Yeah.
I think maybe this is a question for later, but I am thinking about strategic voting, and obviously there's
Aha.
robust to strategic
Yes.
voting, and then
Yes.
how we generalize and like,
Yeah.
okay, yeah.
Okay. Perfect valid question. So there's many properties that I haven't talked about yet about voting systems. There's a lot of people who care about a particular property, which is strategic voting, which is, when I give you my preferences, I lie because I know how the voting system works, and I know that giving you my real preferences is not good for me. Like I can strategically lie in a way such that the result is more close to what I actually care about, and that messes things up completely. I'm not going to chat about it. It's a true concern. For the sake of the argument, I'm going to assume that we have the correct preferences, but this is an important property that we should think about when we record the preferences. Completely agree. Yeah. Yes?
I feel like trying to have the model learn to produce the social consensus choice with probability 1 is sort of leaving on the table the nice thing that we have here, which is a probability distribution in the first place.
I love that you're asking this question, because where I'm going to end up, what the spoiler alert, the solution is going to be a distribution, because actually distributions have some other nice properties. So yes, completely agree with you. Yes, yes. Okay, so now for the sake of yes.
Sorry, just on this, you are going to collapse something that's like, you have this matrix and you're collapsing it into one dimension, because what you want is like a social ordering, or no?
Sorry, what do you mean by you're going to? Oh no, the outcome. I don't care about having a ranking. I care about what is the answer, what is the winner in some way.
Yeah.
So that is one.
So
of
there
the,
is like a collapsing of dimensions.
Yeah, I'm
You're
just gonna.
getting rid
The
of
other
some of
is
it.
just gonna give like.
Yeah, yeah.
I'm being very. I really care about theory, but I also want to be pragmatic in a way that is like, okay, but how do I actually make this work? And I want something that just gives me an answer. I don't want an LLM that tells me like, this is my distribution of the answers, like, or this is my ranking of the answers. Just no, give me the answer. So I'm gonna think in that setup. Does that answer the question? Yeah. Okay. So again, to put everyone on the same page, I'm going to talk about desirable properties in social choice theory. And for those of you who are familiar with the topic, yes, I'm going to talk about Arrow's impossibility theorem. So for the sake of being simple, in the next few slides, I'm just going to focus on voting systems, and then I'll get back to LLMs. Okay, so in the next few slides, this is just about voting systems and nice properties of having voting systems. So a voting system is just a function that goes from the rankings of individuals to a unique ranking. And then the top option of that unique ranking is the winner. Okay? First property that we want. Again, I'm going to ask very basic properties. It shouldn't be a dictatorship, right? And mathematically, this is the intuitive idea that you have of a dictatorship. It's a function where there's one candidate, or sorry, there's one voter, such that whatever the voter says is the outcome, no matter what the rest of people say, right? Like that is intuitive idea of a dictatorship. No, bueno, we don't want that. Okay. Second property that it's very basic and important, Pareto efficiency. That is just fancy words to say, let's go back to the example of ice creams. If every single one of us, without exception, thinks that chocolate is better than vanilla, we should not buy vanilla. That would be stupid. Okay? That is just what this is saying. Pareto efficiency is if everybody prefers A to B or X to Y, if everybody prefers X to Y, X has to win to Y. You should not buy Y. So in this particular example, notice how everyone prefers red to green. Then in the outcome of your voting system, red should be better than green. Third super basic property. Your voting system should not depend on irrelevant things. What I mean by that is, imagine we go to the store, there's only chocolate and vanilla, we're making the decision between chocolate and vanilla in the store, we should not be like, hey, what was Tom's preference over strawberry again? Like, we don't care about strawberry. There's only chocolate and vanilla, right? So the idea is that if you have to make a decision between two options, you should only care about what people think among these two options. Okay, that's what independence of relevant mathematics means. Again, I haven't asked for anything ultra fancy. These are like very basic properties that I'm asking here. And here's the yes.
Does it mean that this option does not exist, or what when you say irrelevant alternative, is
Yes.
this an option that exists but somehow?
Okay, I'm going to be now a bit more mathematical and precise. If we do a voting today with the ice cream flavors that I was talking about, and we do exactly the same voting next year, okay, and people change their preferences over strawberry, but they don't change their preferences over chocolate and vanilla. So everybody who preferred chocolate still prefers chocolate, and everybody who preferred vanilla over chocolate still prefers vanilla. They just change strawberry because whatever. The relative position of chocolate and vanilla should not swap. There's that is the mathematical statement.
So basically, it's a bit stronger than that. It means that whatever strawberry suddenly pops to the top,
Yes,
but the relative.
exactly. Strawberry might win, but if the relative thing between chocolate and vanilla swaps, like there's something that went wrong here. Does that make sense?
Could it happen that suddenly everybody wants strawberry?
If everybody wants strawberry, that's fine, and strawberry will win. It's just that between chocolate and vanilla, they should not swap.
Perfect.
Right? Like you could have strawberry in the first option, but in the second and third option, they should not swap. That would make no sense. Does that make sense?
Yes.
Okay. Okay. Arrow's impossibility theorem. There's this mathematical theorem from the 50s, I believe, correct me if I'm wrong, that says that these super simple, basic mathematical properties are mathematically compatible. If you have more than three or more flavors and three or more people having to make a collective decision, you cannot have the three together. And I know it sounds super counterintuitive. There's proofs on the internet that are like a page. Watch them and convince yourself. I couldn't sleep the day I discovered this because this is so fundamentally depressing. It's like democracy is a chimera, and then what the hell are we doing? Well, we have democratic systems, but de facto they're just pragmatic. They violate one of these, sometimes two. So then what do we do, right? Because the whole point of this, and this is something that I've seen people discussing. I've listened to some podcasts where Amanda Askel, the head of the alignment team at Anthropic, is saying, oh, we should use social choice theory, or social choice theory sounds like a really cool dimension, but there's Arrow's impossibility theorem, so what do we do here? It doesn't seem that is the way. Well, spoiler alert, there might be a solution. So I'm going to give you an intuition of what, yes?
Did we discuss parameter efficiency?
Yes, Pareto efficiency is here.
Yeah.
Oh, Pareto efficiency, sorry. Pareto efficiency is the one where if every single person prefers X to Y, Y cannot win.
Got you.
Yeah. I know that the words are not very clear. Yes?
Can we get around this by having people output numbers of how much they like all the options?
Okay, so we could have, okay, so you might have noticed that here I've been doing aggregation of preferences, assuming that we just have the ranking over the options. Another approach that you could have is, what we have is the level of taste or distaste. It's not only the ranking, but you have a number that you associate with like how strongly you feel about an option, right? And then we could just do a sum of the utilities in some, assuming that here utilities actually mean a level of taste or distaste. There are problems with that. That is one possible approach that you can take, and then we have to answer different questions, which are, how do you learn the level of taste or distaste of someone in some objective way, in some way, and how do you compare level of taste or distaste? And I'm not saying it's impossible, I'm just saying it's very hard, and I'm taking this other approach. That is a possible dimension that, could be taken. I'm gonna take this other one, where like, I give the same weight to, because you could think also like, here's some problems-ish, or you could say, no, this is not a bug, it's a feature. If someone truly have really strong emotions about things, they could become a dictator in some way, right? Like you have the same ranking of preferences, but just you multiply your utility by 1,000,000. Maybe rightly so, maybe not, maybe just by the way that you design the thing, and then suddenly this person is the one that has the whole weight of the decision. But again, like, I could see arguments on like, no, but we should care about that information on level of taste to this taste, and that is fair. It's hard. I don't know how to do it. So yeah.
You go along with that path, we invent auctions, right?
Sorry?
If we go a long way down that path, we invent auctions.
Whoa, but like, what if you have more money than I? I'm not
Yeah.
willing to put as much money, but that doesn't mean that I don't feel strong about an opinion, right?
Yeah.
Like, oh, I'm super hungry. I'm willing to put half of my money on the thing, even if it's just $1.
Let's not invent auctions. Like, let's be clear.
Sorry?
Let's not invent auctions.
Yeah. but yeah, I'm not saying they're not possible directions, and there's a lot of people who worked on that.
I see the difficulty.
But there's difficulties, and if you want to take that approach, you have to attack those questions. But yeah, yes.
Does the Arist theorem actually say, because one of the problems of voting is strategic voting, you don't want, you want to prevent that, is it linked to that? Or
Yes, so I mean, you can, why am I here? This is so later in the talk. Am I moving slides and nobody told me anything? Jesus Christ. Yeah, there you go. So Arrow's theorem just talks about these 3 basic properties. There's so many other properties that we could talk about. Strategic voting is one of them. But again, let's start with solving this huge issue, right? Like, this feels more urgent than strategic voting in some way. Like, but yes, if you cannot even have that, then strategic voting is a whole other issue.
Like this is a problem even without strategic.
Yes, exactly.
Even if you assume you have truthful preference ranking,
Yeah.
it's still an issue.
But yes, strategic voting, and there's so many other properties that people have been studying in social choice theory that I'm not mentioning it, because there's this huge elephant in the room. And let's first solve this, and then we'll worry about the others. Okay, so there's Arrow's impossibility theorem. What do we do about that? And I'm going to give you some insight into what kind of problems people face sometimes with voting functions. This is not a true mathematical counterexample or anything. This is just, examples that give you some insights in what can be going on. This is known as the Condorcet paradox. I'm going to make it even more clear what's going on in here. Let's call each color rock, paper, scissors. Okay? In this example, notice how 66% of the people prefer rock to scissors, and 66% of the people prefer scissors to paper, and 66% of the people prefer paper to rocks. Then what do we do here, right? Like, if you have a voting system that is deterministic, you will have to output a winner, but it feels off in some way, right? Intuitively, you want to randomize, and that is kind of like the solution, and I think that goes back to your point. Yes, we will randomize at the end of the day. So one possible approach that you could take is break the rules and say, no, I'm okay with randomizing. So my voting system will not be deterministic. It will be distribution over the candidates, right? And in this particular setup, it feels that the intuitive solution should be give the same probability to each of the 3 options, okay? Now, there's this really cool paper from 5 years ago that I don't recommend you. Yes?
Is this kicking the problem up a level, though, where now people have preferences over probability distributions?
Yes,
and how do you
okay.
integrate those?
Okay, so there's this result that makes an assumption, which is like, if you have preferences over things, then the preferences over lotteries over those things has some structure, and it's a structure that kind of makes sense. And then we could enter into behavioral, and you could think about like super weird, funky preferences over lotteries that are like, oh, in this particular example, then it breaks, and like, fair enough. Some of them are more reasonable than others. So there's an assumption in the following rest of the presentation, which is the preferences over your distributions are nice in some way. If you prefer more chocolate to vanilla, 90% of chocolate, 10% of vanilla is better for you than 50% chocolate, 50% vanilla in some way, right? Like, they're making some assumptions like this hidden here. If you truly want to get into the tiny details of the mathematical assumptions, you should read this paper. But this paper is obscure as hell in the sense of like, I read the paper knowing what the punchline of the paper was, and I still didn't see the punchline. like, I'm going to tell you what the punchline of the paper is. The punchline of the paper is there's one and only one stochastic voting system that satisfies the axioms from Arrow's impossibility theorem. And that, I know, it's, and that stochastic voting system is a voting system that has been discovered and rediscovered again and again over the years, and it's called Maximal lotteries. Okay? So now I'm going to make a normative point. Maybe we should use Maximal lotteries to align LLMs. Right? And this is a normative point. You can have a debate about it. I know there's people who have different philosophical views on how we should align LLMs with people when people disagree, but let's just roll with it for the rest of the presentation. Yes?
Yeah, I was just going to ask, you know, there's a lot of stuff in decision theory in like different contexts that show that if you have some options, you can't do better by randomizing, right? Like there's no, there's like the best option by your ranking. You might be indifferent between a bunch of things, but by randomizing, you can't actually do better. So I'm kind of curious how this is supposed to be optimal. Is it a different sense of optimal?
I don't know about exactly which particular. I would love to. Do you mind if after the presentation we go into the whiteboard and we go
I would
full
dislike
deep
it
into
if
the?
we didn't go into the whiteboard.
Of course. Sorry. Of course we will go into the whiteboard. Yes. Okay. So let's take this offline. I'm really curious about this. I don't know exactly which point it is, but like we can clarify it later. So yeah. Okay. Something that whenever I present this, something that people say to me is like, oh, but randomizing could be very bad because like maybe we give something that only 1% of the people want, which is a horrible thing. And I'm like, wait. Randomizing doesn't mean that you choose anything. You could give probability 0 or probability 100 to some options. That's still a distribution, right? So just to give some intuition, in the previous example, imagine there was an option that everybody hated. The maximal lottery will give probability 0 to that option, which feels natural, right? If there's an option that is the Condorcet paradox, that option will get 100% probability. So if you have a, if there's an option that is the Condorcet winner, like Bulbasaur in the previous example, that option will get 100% probability. So when there's a clear winner, 100% probability of the clear winner. When there's a clear loser, a 0% probability to the loser, or an option that is dominated by another option. When there's a debate, you randomize. When there's a paradox like this one, okay? Okay, now back to LLMs, because I haven't talked about LLMs for a while. What the hell are we doing right now? So what we do right now is LLHF, reinforcement learning from human feedback. How does that work? What you do is, you go back to reinforcement learning setup, and ideally what you want to do is, I want to work with reinforcement learning, so I need to give points to statements. And then once I have a way to give points to statements, I'll just maximize points, right? So we would love to have a machine or a human that gets a question and an answer is like, that answer is 700 points. And then we're just like, okay, I'm going to keep changing the answer until I get 800, 900, and try to maximize that. However, doing this is very hard to do. It doesn't scale. So what we do instead is we collect data sets in the following way. We show people questions and pairs of answers. And we tell them to pick one of them according to different criteria. Right? Like, which one do you like the most? Or which one is more offensive, less offensive, more helpful, less helpful, or whatever. For the sake of the argument, let's just say they pick whichever one they prefer, in general, okay? And we do this tons of times, and we have our data set. And then with this data set, we try to infer the points machine. So hidden here is an assumption that is called the Bradley-Terry assumption, which is an assumption that says, I know how people choose one option over another. I know the particular probability distribution that they use, right? That is the Bradley-Terry assumption, which is basically saying this is the probability, like this thing is the probability that y plus is preferred to y minus. And if you do that assumption, you can just do maximum likelihood. So first step of LLHF, to maximum likelihood, estimate R, where R is the reward or the number of points of each one of the statements. And in the second step, you maximize reward. The formula usually has this other term, which is just regularization, but that's basically you do. Estimate, machine that gives points, maximize points. If you look at this method,
Here's a question. Before we were talking about what if you add numbers and you have people vote and then you're like, it's kind of hard, you can multiply by things. You know, it's kind of like a certain kind of scale type. What is the assumption of the scale type here? Are you assuming it's like an interval scale, like utility, or is it like a ratio scale, like?
The assumption that is hidden here is the Bradley-Terry assumption, which is it's not an assumption about the. You're not assuming that. I don't believe there's any assumption about the utility form or anything like that. You just assumed people have the same set of values in some way, and the probability of one statement being preferred to another statement is this formula. And you have that particular function of like the probability that statement A is preferred to statement B by society is 70%, where this number comes from e to the r statement 1 minus r statement 2 divided by no, sorry, whatever. I can write the formula here.
If I multiply r by like an arbitrarily large positive number,
It will
or
change
like
the
I add a
probability.
constant, it does change the
It does change the probability. If you multiply this by 100 and this by 100, they will get more distant, and the probability will get more extreme, and that will mean people choose y plus way more often than y minus, right? Like it's not you cannot just scale r. Yeah. Yes.
Should we think of this as structurally analogous to something like logit choice, where you have the kind of rationality parameter, where if you scale them up, at one extreme you begin to approach something like best response, at the other extreme you get perfect randomness?
Can you clarify that again? Should we?
So,
Yeah.
with logit choice, sometimes called logistic choice,
Yes,
right, where
yes.
you have the exponential distribution,
Yeah.
and you have the parameter in the exponent.
Yeah.
It can be conceived of as a rationality parameter,
Mhm.
where you'll get the kind of sigmoid function in intermediate values, but
Yeah.
at one extreme you'll get basically a convergence to strict best response.
Yeah.
Another
I
randomness.
I think that this touches again back to this hidden assumption that I said earlier, which is like, when people don't consistently choose the same thing, that is noise, or that is people not being rational. And I'm like, no, maybe people deserve, because here we're using different people's opinions on the same question. And if they imagine, I'm gonna make a super stupid example. What is the best animal? Dog, cat, and like 70% of the people say dog. You won't say, this is because of noise, or this is because like they're not rational. It's like, no, there's people who prefer dog and prefer cat, and you're just aggregating them. And by doing the aggregation, that's where you get the noise. Like, I think that, you can impose that theory, but what I'm saying is like, you can view the world in this way where like that is coming from noise or lack of rationality. I say we should drop that assumption completely, and you just accept that there's a percentage of people who, like the interpretation that I give is there's a percentage of people who prefer an option, a percentage of people who prefer another option. Don't give a functional form to the thing, and just be aware that the noise or the fact that the probability is not 100% comes from people disagree. Does that answer the question?
But beta is an entry parameter, right? Beta is saying that like we don't always want to output I love pizza because the number of people agrees on this. You also want a little bit of the base model objective, right? And it's competing against the reward objective. No.
Can you say that again?
So my understanding, beta is an entry parameter. So like.
Sorry, beta. This beta?
Yeah. So it is.
You were talking about this beta?
I would.
Oh, you were talking about this. I was talking about. Okay, sorry, but you're talking about beta. Sorry. Which is different.
Then I'm saying.
No, but still, that might be a fair point. You're saying, but we still want.
Like we have competition of like the base reward where you want to complete text as text, and the RLHF reward, which is you want to always say I love pizza. Right?
Okay. Yes. I think that this points a particular issue that RHS has, which is RHS converges to not a distribution but a spiky answer. Like it gives probability 1 to an answer, like pizza, 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 pizza.
Well,
and we could.
That's beta. Well, if beta is 0, right?
If beta is 0, yes. Like if you don't put this, if you don't put the regularization, you will converge to I just give the answer that maximizes the reward, and that doesn't feel natural in some way. And then you have to add this patch, right? I'm saying that's a nice thing of maximal lotteries. Like you have that noise by default. You're not adding a patch. Also, why is the distribution that comes from pre-training normatively good in some way, right? Like you're having a middle point between saying pizza, 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 pizza all the time, and then whatever the distribution of food was in the pre-training. It's not exactly like that, but I'm making it extreme so that it's clear that there's a problem in like regularizing and putting this patch just to enforce distribution. Yes.
I now understand it. I was wondering what if the reference is broccoli.
Yeah. Where does the reference come from? Like, we're putting this because otherwise we collapse to distributions that are like not nice in practice, and then we have to ensure that it's a distribution, and we do this and all the regularization.
The answer here is also normally when you do that properly, you actually want the reference to be. It can be done, for example, in reinforced coding, and then you want the reference is actually marginal of policies. It's a long story, but
Yeah. I mean, you can do many fancy things here, but then it's like the question comes, then why are we doing this middle point between this thing that you have this fancy thing and this thing that you like? It feels off to me in some way. Like, I'm not saying that the techniques that I'm going to talk about at the end also use this, just to be fully transparent, because like we still don't have a perfect way to find the true preferences of everyone, and there's still problems on the regularization. But like, just I think that if we really care about alignment, we should really think about like what the hell is this doing. But anyway.
Well, I mean, like there's a standard answer. There's actually a paper that discusses what this is doing, which and the standard answer is that it's like that the model is also trying to speak well, right? Like it's like trying to complete the text. So it's like maybe I can find the paper, but
Yeah.
Like, it's like you do want the model to like say things that are like grammatically correct and generalized and.
Yeah, like I understand in practice why we do this, and also there's problems of like this is not truly the reward. This is just an estimation, and then what's going to happen is that you're going to do reward hacking otherwise, and you have to regularize because otherwise you reward hack, and that's not bueno, right? Like I understand that we do this, and I think it's good. It's just in the long run, when we think about scaling this up to the infinite, we have to think about like, okay, what is this doing in terms of like alignment?
I actually think the regularization, but let's
Yeah.
cover it later, is actually one of the big biases that people put in the models.
Yeah.
And so I don't think it has been treated very softly.
Okay, so I should go a bit faster. What are we doing right now? We're doing LLHF. Okay, if we put our social choice theory classes, what is LLHF? And this is a really cool result from last year. You cannot see it, but it's an ICLR paper that I don't know. So basically, their lemma result is not the main result. Their lemma result, I think, is the coolest part of the paper. And what they say is, oh, LLHF actually behaves like a voting system that we understand, that is called board account. And board account has been a voting system that we've studied for decades, and we know the good things of board account and the bad things of board account. Board account is this system where like when you have 3 ice cream flavors, you give points to every flavor. You're like, I prefer chocolate and strawberry than vanilla, so you give 3 points to chocolate, 2 points to strawberry, 1 point to vanilla, and then to decide which ice cream you buy the ice cream with the highest amount of points. That's what board account is. And board account violates a lot of super basic desirable properties. And I'm going to talk about the problems with LLHF once you have this lens. And then I'm going to make the normative point, which is like, okay, so maybe we shouldn't do this if we're thinking about pluralistic alignment, because it behaves like this voting system that doesn't have nice properties. We should do something else. And again, normative point, and we can have a philosophical debate, and we should talk about it. We should do like a maximal lottery. We should try to approximate LLMs to maximal lotteries, or something that is a variation of that. I also have some thoughts on the limitations of this, and I will talk about it at the end. And let's roll with it. Let's say, okay, we want to do that. Then how do we actually do that? Is this just a theoretical exercise, Roberto? Or can we actually implement this in some way? And here's the cool part. So I did this super simple proof. Is like, but this proof arrived to something that already existed. It's like, oh, a lot of people already found this formula. Like, and I'm going to give you some intuition on what is the method. The method is called so we arrived to a formula. This is exactly the same formula that some other people have been proposing at DeepMind in a paper called Nash Learning from Human Feedback. They never talked about social choice theory, but it still behaves very well, scales really well in their papers. They compare it to LLHF in a lot of metrics and benchmarks, and like, they show that indeed it's a very promising method. So how does it work? You have 2 LLMs fighting against each other. And you give a question to the 2 LLMs, and they each give an answer. And they're playing this game where like they're gonna show both answers to all of you, and you're gonna vote which one you prefer. and then you're going to give points depending on the amount of votes that you get, right? And because it's a game and it's symmetric, there's a mix strategy in Nash equilibrium that is symmetric, and spoiler, that mix Nash solution happens to be that voting system that I was talking about. It's just pure coincidence.
And it's unique. It's convex.
Sorry?
It's convex, so it's a unique Nash.
Is it unique? I want to say there might be some situations in which like it is. I'm sure that in a lot of situations it is unique. I just want to be vague because I haven't made the proper assumptions. But yes, I'm most likely, without thinking super hard into it, like I agree with your intuition that most likely it is unique. But I don't know. Because like, again, we will have to make some simple assumptions, but yeah. Okay, so just to give some more intuition on the formula. You have two LLMs that are fighting against each other. You're going over all statements. There's LLM1, LLM2. LLM1 goes over all statements, LLM2 goes over all statements. Then you have the percentage of people in your society who prefers statement A to statement B. Okay? And of course, there's some people who are indifferent among statements. And then you have here the probability of one statement being preferred to another statement. This is the probability that the LLM1 says statement A. This is the probability that LLM2 says statement B. So if I know that you're likely to say paper, I'm gonna be very likely to say scissors if I know that a lot of people prefer scissors to paper. Does that make sense?
But why is the second term reasonable? Like, if B really doesn't like scissors, then like that means they're weighting this term very low when in fact they're usually weighting it.
If
Right?
sorry.
So maybe I'm
Oh no, but you're fixing the probability of the other one. There's a max and a min, so you will adversarially play against me.
Oh, I see. Yeah.
Right, like this is a game. It's
Sorry.
not. There's the 6 distribution,
Pi is
and we
not-
try to play against this distribution.
Pi is
No.
not the Bradley
We're
Terry
both
model.
playing a game.
Pi is not the Bradley-Terry preference.
No.
Sorry.
Pi is an LLM. Pi prime is another LLM. I'm an LLM. You're another LLM. I'm gonna choose probabilities over the statements. You're gonna choose probabilities over all the statements. This is the points that I get.
Pi
You
is
get
strategy.
1 minus that.
Pi is a strategy.
Does it make sense? Okay. Technically here I should write arc because it's the arc maximum of this. And this is the solution. And what we found, is like something that has been rediscovered again and again and again. And there's so many papers that has this formula or very similar formulas, which is great, right? Because, so basically, if you make an extra assumption which is this never happens, or it happens with density 0, or a more reasonable assumption, which is if people are indifferent between one and the other, they will pick one or the other with 50% chance, which I think it's a fair assumption. You just have to maybe randomize the order in which you present things. Then you can drop this. You have this formula, and this is the formula that appears on this paper. And here's the cool thing, right? Like, now this is not just theoretical. This is a method that appears in a paper where, like, these people are engineers that only care about post-training LLMs in a way that they behave well in whatever the metrics they care about, right? So being pragmatic, this is something that they've talked about, and they're like, oh, this actually works really well, right? Like, there's a bunch of papers after this one that kind of like continue this work of having this optimization process that works, really well. And there's libraries out there that have open source implementations of this. So there's this library called TRL, where you have the method in this paper, which is called NashND, and other variations. To the best of my knowledge, the latest iteration of this is a method called Online IPO that also performs this. For those of you who are like super into the tiny gritty details of implementation and like making this scale, I recommend you to check those papers. Again, that's their jam, that's the kind of things that they're into. They never chat about alignment, up to a point, right? But they never chat about social cheese theory, they never think about pluralistic alignment, that's not what they will talk about here. This is kind of like our result. The result was like, oh, that cool thing that they're doing actually behaves like this cool pluralistic alignment method, okay? Which I think is great because it's like, okay, this is not only something theoretical, this is something that we can start to chat as a pragmatic thing to do. And then we did some simple experiments, super simple. We're now doing a better iteration of those experiments that is more reasonable with the harmfulness, helpfulness data set, but just, I think that still this kind of like makes the point in a transparent way. So there's these simple experiments that we did to show the problems of RLHF and see how Nash learning from human feedback and LHF outperforms them. So imagine the situation that I described before, the rock, paper, scissors situation. Okay, if by noise one of the groups is slightly higher than the other, or just by noise in your convergence process, your reward of one of the colors happens to be slightly higher than the reward of the other ones, right? What's going to happen is that in your second step, you're going to just try to maximize the reward, and you're going to have an LLM that just says green, right? When it doesn't seem fair in some way, right? Like you look at this example and it's like, it doesn't seem the intuitive solution that I want to say green 100% of the time just because of this small noise or whatever. So that is one problem. Also, RLHF collapses if you're not careful. Right, like you get these distributions that poop collapse to one, and that's what you have to regularize. Right, you have to put early stop, you have to do cat regularization and other things, among other reasons. I'm not saying there's not a lot of actual good reasons to do that, but like that's one of the things that you have to be careful about. If you do NLHF, what you would expect to have at the end of the day, it's a distribution that is 33%, which is kind of like the kind of like intuitive solution that you would expect here. So we did the following super simple experiments to kind of like get the point super clear. We created a population and a data set where there was only one query, what is your favorite color, or variations of this, and there were only two kinds of answers, that there were always colors from here, red and blue. So basically you pick two colors, you pick a random individual, that random individual picks one of them according to their preference, and that's one point in our data set. And we created a data set like this. And then we train an LLM with this text, with both RLHF and NLHF to see what will happen. Does the theory actually apply in practice? And what we observe is, yes, if you have a situation like this, what you would expect, as I said, is RLHF giving probability 1 to one of them randomly, and NLHF giving a distribution over the three, and that is indeed what we see. Here, if you train with RLHF, the x-axis is the steps over training, y-axis is probability. The model was a GEMMA model. Immediately, one of the colors gets probability 1 during the training step, which was the color that had higher reward. If you do NLHF, you converge to a mix among the three. Another problem, yes?
So is this chart for the rock, paper, scissors? Or
Yes, this is for this particular example.
Okay.
A population that looks like the following, if you train with NLHF, will give you a distribution that looks like the following. Another second experiment that we did, and this is the one that it struck me the most, and this is the one that I'm most amazed that worked. So imagine the following situation. You have these individuals, okay? And again, the question is, which color should we paint the room, or something like that? The majority of people prefer blue. If you train an LLM with RLHF, red would win. Even though the majority of people prefer blue. If you train with NLHF, blue would win. So you will converge to giving blue probability 1. Another example is the IIA. Another one that when you say it out loud feels very weird. If you add extra tokens, extra statements that are irrelevant, you can completely swap the answers from the LLM. So if you have a preference like this, and you don't have the token green, or green doesn't appear in the dataset, both will converge to say blue. The moment you add green, it's not that it swaps to green, which then maybe I would understand. It's like it swaps to red. And red was already an option here. It feels so weird in some way. I added something, and that something changed the answer in an irrelevant, like the green is completely irrelevant here. You're swapping from blue to red just because I added green? That doesn't make sense, right? Like that, the intuition here is like RLHF could swap the answers just by adding points to the data that are irrelevant. And here are the plots of our experiments. So on RLHF, first we have with 2 options blue, with 3 options red. NLHF consistently over 2 options and 3 options, we have blue as the preferred answer. Now, if you're curious about the implementation of NLHF and scaling these and so on, I would really recommend you to watch this YouTube lecture by Daniele Calandriello, who is an engineer. I don't know if he's a research scientist or research engineer he's a researcher at Google DeepMind working on post-training of neural network, and he's one of the main authors of that literature. He covers basically all the literature of NLHF, and he gives his thoughts on why it works well. But again, he never chats about social choice theory. These papers are papers that care about no, we care about the implementation details, the scale details, something that has good performance on the classic benchmarks and metrics that we usually care about. And then conclusion and next steps and some limitations. So what we showed is that National HF, which is this set of papers that are out there, actually behave like Maximal lotteries, which in some normative sense is the best voting system. And we showed experimentally that it outperforms RLHF in some examples like rock, paper, scissors. It actually satisfies the preferences of the majority. It is not, it does not violate independence of relevant alternatives. Now, some limitations and some thoughts that I have about this. Next work. Some of you might say, I don't care about the majority, I care about those who are worse off. And fair enough, I could see that philosophical point being thrown, right? Like the tyranny of the majority. If you want to do this, I feel that an approach that you could take is estimate utility functions. You have to have a level of taste or distaste. This is hard, but hey, it's not about what's hard, it's about what's ethically. And if you do that, then it's about maximizing the utility of the one that is has the minimum utility or something like that. Still, I think that there's a lot of literature in social choice theory and economics that is very relevant for that kind of question. I've seen a paper or two that tries to attack this, but they don't. The problem is that people confuse a reward function with an actual reflection of your level of taste or distaste, and then it gets very tricky. But anyway, that's one possible criticism that people could have, and that's fair, right? As I said, we can have philosophical debates about what is the best thing to do. Another thing that people kind of have pointed out, and I completely agree, is what about personalization? If I chat with my LLM, I want my LLM to chat according to the kind of things that I like and in a language that I like. I don't want the average democratic answer. I'm fair. I think that it should include in some way, the preferences are not fixed preferences. What does it even mean to prefer A to B? And I think that it should include in some way information and context, who are the relevant individuals here, right? If we're doing a decision about the library in a city and we're going to paint the library, the relevant people are the people from that city. If we're thinking about you as an individual, the relevant people is you, and maybe you want to do this thing with people. You could still think about this as a technique. You could still think about this as a technique of personalization, where you're looking at people who are like you, but then you have to have information about when are you talking to someone, when are you doing an action that represents something that is going to affect multiple people. This is just to say they don't have to be conflicting goals, personalization and pluralistic alignment, right? Also, the context is important. There's people at DeepMind who have been thinking about this idea of theory of appropriateness. Something might be appropriate now, might be inappropriate later. If I'm chatting with my LLM and I'm chatting with some friends and I'm look what the LLM says to this, I want it to say funny things and jokes and stuff. And if I'm in a professional setup, I want it to say something in more a professional tone and more serious, and that depends on the context, and my preferences might change with the context. And I think that is something that it's it feels to me like an engineering problem, right? Which I'm not saying is not important. We should definitely take that into account. It's just, okay, so our preferences are not fixed. The preferences depend on the context and on who's the relevant individual. Yes?
As someone who's very theory, not very ML, I have an intuition that you could just do this by redefining what you mean by A and B. And so do I want to eat if I'm hungry, if I haven't eaten, or the things that I want depend on context, but then my choices are the things I'm choosing include the context,
But then if I'm if I'm hungry, I want a small snack. If I'm not hungry, I want pizza, and then I have many options. But then you have to create a relation between what do you prefer, having a snack and not being hungry, or having a pizza and being hungry. And it's no, but I'm hungry or I'm not hungry. So you need to fix the context, I think.
Okay.
Does that make sense? I don't know.
Yeah.
Or maybe I'm not understanding. I could also be missing
No,
out.
I think this is right. Maybe this is something like the conditions that you put on when I need to have preferences, like I assume complete preferences. You don't need to assume complete preferences across different contexts or something.
I mean,
because that's what you're saying is like
yes,
you need to have
yes.
complete preferences. Because I was thinking then
it just feels. I mean, I'm not saying it's important. Again, we can chat more about this offline, but I feel intuitively that starting to play with incomplete preferences can get very tricky.
no, I agree.
And like, if I'm being pragmatic, I'm like, let's have complete preferences. Let's just have preferences that are continuous depending on the context on some way, right? Like, depending on the context, these are the preferences. And then I'm like, okay, what is the context? Okay, given this context, these are preferences. Therefore, this is how we maximize them or something.
But I guess I don't mind about like if across context, if it doesn't matter what my preferences are across context, I can just arbitrarily complete my preferences. And so like I don't think this is an issue. You still have I prefer pizza when I'm hungry over no pizza when I'm hungry. Like this is a preference, and then I prefer no pizza when I'm not hungry over I prefer no pizza when I'm
I'll
not
have to
hungry.
think about it.
Okay.
I don't know. I don't feel
think
comfortable
it's
answering because like I have to give it some thought and I don't know.
Sure.
I don't know at the
Sure.
moment. Yes.
So I'm not sure if I'm just asking the same question in a different way, but like whatever optimization objective you were showing earlier was about the loss for a y conditional on an x.
Yes. Yes.
So like we're already conditioning on some stuff.
Yes.
And person and context
Yes.
can just be part of
Yes.
that x, right?
Completely
It's
agree.
not gonna change.
Completely agree. I'm not thinking this is something super drastical. Yes, completely agree. I'm just saying, hey, this is something that we have. This is a common concern that I have. This is a common concern that people express to me when I present this work, and I'm saying,
Like mathematically, it's unlikely.
yeah, it doesn't feel that crazy to me to just add it as part of the.
Yeah.
Here you have X, which is the question. You know, who are the relevant people and what is the context? Like, I don't think it's that crazy to imagine that we have a vector embedding here that it's the input that you pass. Yeah. So I completely agree with you. I don't know if I'm over time or not, but like, yeah, I'm more than happy to keep answering questions.
1 minute.
Yes, 1 minute. Okay, so any more questions? Yes.
Would you mind going back to the full version of that equation?
This one?
Okay. Yeah, I'm wondering if there's a nice geometric lens here, because it looks like a vector times a matrix times a vector.
Yes, yes,
So
yes.
it's like you pick, it's like there's this fixed matrix in the middle that has to do with the landscape of people's preferences
Yes,
over stuff.
yes, yes.
Since it's symmetric, I'd be interested what the meaning of the eigenvectors of that thing are, like some sort of direction and preference space in this.
I don't have an interpretation for you right now. I never gave it that thought. There might be some interpretation to give to like the different vector directions in this matrix, but I don't know at the moment. I don't know.
Might be cool.
Yeah. That's a fair point. Yeah. I never thought about it. Okay, thank you. Any other questions? Okay, well, thank you very much for your time. Really appreciate it.